So let me start the explanation by explaining engines. So all heat engines all heat engines. So let me start by explaining heat engines. All heat engines exploit temperature gradients. Do we all understand the word temperature gradient? What is a temperature gradient? Difference of temperature. So all heat engines must have a source at higher temperature and a sink at lower temperature. H is for hot, C is for cold. What will happen between hot and cold? Temperature will flow from hot to cold. What if while it's moving from hot to cold, we put a paddle wheel in between? What will happen? It will start to turn. What if on that paddle wheel, I put an axle? It will turn the axle. What if I put a wheel on the other side? It'll spin the wheel. What if I put a car on top of that? It will drive the car forward, right? You see it? That's how power plants work. So it must have a source of hot, it must have a hot source, and it must have a sink to which it can eject the rest of it. These are also called hot reservoirs. And these are called cold reservoirs. And why are they called reservoirs? In thermodynamics, the reason why we called it, what is a reservoir? Something so large that if you take something off of it, it doesn't really change its temperature. When we talk about hot and cold reservoirs, we also can talk about heat in them, that they are allowed to give and receive, which is given by TH delta SH. Do we know where this is coming from? Good. What was that called? Yep, from the second law, right? Entropy. From our definition of entropy. So that means I can redraw this. May I redraw this as this? So I will have a hot source at temperature TH. I can put a paddle wheel in here or an engine in between. And that paddle wheel can give me some work out. And then I can have actually, let me make this as a dark blue. And then I can have a cold sink here at T, temperature T. So then I can rewrite this as heat can flow from the hot source part of it will be used to do work, and the rest of it will be ejected to the sink. And this is what I'm calling my engine. So then am I mathematically allowed to write this? Everybody okay with me writing that? So what is the one thing I'm concerned about when I talk about engines, cars? What's the one thing that we worry about when the gas prices go up? Money too, yeah. But what do we all worry about? Yes? Fuel consumption? That is called efficiency in thermodynamics. How much useful work can I get from my input? And there's a symbol that we use. It's called eta. All that means is efficiency. How efficient are you in terms of business, benefit over cost? That's how that's how business people look at it, right? What's my benefit to my cost ratio? Okay, in terms of thermodynamics, we call eta as useful work divided by heat input. What's the symbol for work? W. What's the symbol for heat input? Q, which one? There's only two. It can be either H or C. Which is input? H. Are we good? May I rewrite this as QH minus QC divided by QH? Or eta will be given as 1 minus QC over QH. May I also, from equations 1 and 2, because remember, I can't quite figure out QC and QH. Wouldn't it be just easier if I could just do temperatures? So may I, from equations 1 and 2, instead write this as and for reversible processes, ideal scenarios, may I get rid of the delta S's? Only for ideal reversible processes. So when you see this equation written, understand that this is for ideal reversible processes only. So how do I get the efficiency to be 100%? If I make my ratio TC over TH very, very, very small, ideally 0, can that happen? In order to do that, what I'm trying to tell you is that all of the heat that I had is going to be converted into useful work. Does that happen? Ever? No. So no real engine will ever be 100% efficient. Right? So also note, whenever you do these problems, your TC and TH must be in Kelvin. Must be in Kelvin. T's must be in kelvins. You would think, but you would be wrong.
Yeah.
No, it's actually true. Even though it is a ratio, it must be in Kelvin because the numbers change depending on whether you're using them in kelvins or in degrees Celsius or in Fahrenheit. So make sure if you want to get the answer right, make sure this is always in Kelvin. Kelvin. So for example, take TC equals 300 Kelvin, which is about room temperature, and take TH to be about 500 Kelvin, which is what? Yeah, in Celsius.
27 degrees.
500 Kelvin?
500?
So this is about room temperature.
Celsius.
What is it?
A little bit more than 227 degrees.
227 degrees Celsius. So if you had an engine at 200 degrees Celsius and you had to eject your heat to room temperature, about 20 degrees, give or take, figure out what your efficiency will be. $300 divided by 500? 0.4. So it's about 40%, which means what? 60% of the input is wasted.